All right, party people. Exam tomorrow. I
Uh,
had a, what's that?
Yay.
Oh, okay. I had a few, why isn't this? Oh, sorry, I'm having a better. There we go. So I had a few emails. I tried to respond to some emails about, some of the different things. One of the things that I thought, which is a pretty good question, is we can do a transfer function example. And a transfer function, okay, if you don't recall, the whole purpose of a transfer function is to be able to transfer the input to the output. The input is usually the power supply. Okay. The output is whatever signal I'm interested in. So a transfer function for a circuit could be I could have this crazy complicated circuit in here, but I could replace it with a Z in the Laplace domain. I could just call it Z of S. So one of the things you could do is just write some bunch of circuit analysis equations so that you're getting a transfer function that gives you the output, whatever you're interested in, based on an input supply. And again, the whole reason why we do transfer functions is because we don't necessarily know what our inputs are going to be. All right. Obviously, like if we're running a laptop, I mean, a benchtop power supply where we can energize things and we can do things, we can pick the input. But once you get out in the real world, there's no guarantee that the input that you think is going to be there is in fact going to be there. Things change, people do stupid things, it just happens. And the more important the system is, the more you have to analyze it to consider all these out of tolerance expectations. So your transfer function allows you to do that generically, and you can look at all kinds of different conditions and cases regardless of the input. So it really is telling you more about how the system is going to respond to various stimuli as opposed to knowing exactly what the output is going to be based on a given input. So it's kind of a just a general way to approach it. Okay. So I have an example, tried to make it a little more complicated. So here's my capacitor. That's 3/2. Here's my inductor, 4/3. Another capacitor, 1/2. And another resistor, that's 1 ohm. And the signal of interest that I'm interested in is V2 of T. Okay. I can't actually solve for V2 of T because I have no idea what V1 of T is, right? Or Vn. So this is a perfect application to go ahead and do the transfer function because once I have the input signal, I can convert it to the Laplace domain, multiply it by the transfer function, get an output, take that to the time domain, and then I know what the output's going to be. I'm not stuck at any specific input, which means I would only be able to give you the answer for that very specific case. So because this has a bunch of inductors and capacitors, which would require us to do integrals and derivatives, I, at this point, can't do a transfer function in the time domain. Remember how we did negative RF over RI? What did you call that when you were taking John's class or your circuits class? You called it the open loop or the closed loop gain, which is another way to say transfer function. For DC, that's the transfer function. When we have resistors and inductors in it, we can't just do that. So let's take this to the Laplace domain. So what does a capacitor look like in the Laplace domain?
DS.
1 over CS or
Okay, 1 over CS.
2/3 S,
Mhm.
right? What does an inductor look like in the Laplace domain?
LS.
L times S. So this is 4 over 3 times S. Oops. And a resistor just looks like a resistor.
Mhm.
Here's V2 of T. Here is V1 of T. I said V1 of T. V2 of T should be V2 of S. All right, so now you can do any circuit analysis technique that you want to go ahead and find the transfer function. So my transfer function in the Laplace domain is going to be V2 of S over V1 of S. So I have to write an equation for V2 of S over V1 of S. So you tell me, what circuit analysis technique would you like to do? I
Nodal
have one
analysis.
that I would suggest, but you get to pick.
Let's do nodal analysis.
Yeah. If you do nodal analysis, right,
Yeah.
you have a node here, and you only have one node there. You only got two nodes. And the first node, this is V1 of S, right?
Yep.
And the second node is V2 of S. So if I do everything from a nodal analysis perspective, I don't have any other variables that I have to tease out. I've got everything as a function of V2, or not as a function, but everything multiplying either V2 or V1. Okay? So doing nodal analysis is the fastest way to do this. But you certainly could do series parallel combinations if you want, right? You could put these two in parallel and then do a voltage divider if you want. You don't have to, but if you wanted to, you could do that. So let's do nodal analysis. So we'll assume some currents here. Okay. And I'm only going to do nodal analysis for V2, not for V1, because I know that that's V1 of S. Whatever the input signal is, has to be that voltage. So why would I even bother doing a nodal analysis at V1 when I know what the voltage is? So I only have to do nodal analysis for V2. So the current into the node is V1 minus V2 over 4/3 S, right? That's the current through there. That's the current in, and then the current out, V2 divided by 2 over S plus V2 divided by 1. Any, Luke, question?
Why do I think it's V2 minus V1 instead of V1 minus
Anybody want to help Luke? He said, why does he think it's V2 minus V1 and not V1 minus V2? Henry caught this last class, right? So we assume correction of current is left to right. So to get a current direction from left to right, we got to take the left voltage and subtract the right voltage. That's the voltage drop in that direction. If we did the opposite current direction, then it would be V2 minus V1. Okay. Did that answer your question? Okay. So now let's do some fancy dancy math. So I have V1 over 4/3 times S equals V2 times 1 over 2 over S plus 1 over 1 plus 1 over 4/3 S. If I just move things around a little bit. Any questions on that? Let's clean this up a little bit. So V1 times 3 over 4S, all right, equals V2 times S over 2 plus 1 plus 3 over 4S. My common denominator on the right-hand side is 4S. So that equals V2 times 2S plus 4S plus 3 all over 4S. V1 times 3 over 4S is going to be equal to V2 times 6S plus 3 all over 4 times S. So V2 over V1 is going to equal to 3 over 6s plus 3. Which is equal to, let's see, 1/2 times s plus 1/2. That is the transfer function for this particular signal.
That would be easy to take back to the time domain.
Mm-hmm. Got that? How to do the transfer function? It could be. So this is the transfer function for V2 over V1. But I could say, no, I actually want the transfer function for I1 of S. So what if I said this? You just redo the work to have it expressed as V2 divided by I1. So now you have to write all your equations as a function of V2 divided by I1. Or you got to write your equations so that you just have V2 and I1. So that one would be something that'd be a little bit different. It would end up with a different transfer function.
Why, and I see the algebra, I see like where,
It's not an element. It's a bunch of elements. It's here. It's all these components combined so that you no longer have individual resistors, inductors, and capacitors. It is just a network that you have one element, if you will, one make-believe element that includes a bunch of resistors, inductors, capacitors all put into a block or your transfer function. So instead of having to build a circuit that looks like this and testing it out, I can just go and plot this in Excel and get results. That's how you do this. Make sense? Want to see another one, or you want to practice one yourself? All right, so give me this one then. Give me the transfer function for V2 in relation to I1. Don't want I1 anymore. I don't want V1 anymore. I want I1. So do the transfer function. I'll give you a hint. It's easier if you do nodal analysis.
Can you scroll down just a little bit so I can grab V2?
I'll zoom out.
Okay.
Keep going or?
Yeah, yes, I can see the V.
Okay.
So I think the little markers are covering up what I want to see.
Oh, I don't know how to move them, but let me see if I can shrink them. Is that good?
Yep.
I will apologize for Tuesday if anybody wanted to come find me. So pretty much right after class, we lost power in this building. I don't know if anybody knew that. And then there was also a steam line break right next to my office. So we had to clear out. I was working in my office until the steam broke, and then it was like a whistle, but also became incredibly humid because steam was getting dumped in there. So if you walk down the corridor, you'll see all the like the papers are kind of folded over because they got saturated with water from the steam. And it was just like we had to get out of there because it was getting like a sauna essentially in there. So we had to vacate. So I was planning on leaving at like 12:15, 12:30, like normal time. Well, until campus was closed, but with the loss of power and the steam break, it was like, yeah, this is an omen for telling me to go home. So I left. But I apologize if anybody was looking for me on Tuesday afternoon. There were just two things that I couldn't handle. I will be here today. Anybody get the answer?
Getting there,
So you want a little more time?
please.
Okay. Is anybody stuck? Couple people? Who's stuck? So most people, so Arthur, you can ignore, turn down the volume, I guess, and you can just ignore what we're going to be doing because there's almost everybody here in the live session is unsure of what to do. So let's go back and redraw our circuit, but it's the same exact circuit. So this is 2/3 S 4/3. I'll put the S up here so there's no confusion. 2/S 1. This is V2, this is V1, and this is I1. So you remember how we didn't have to do nodal analysis for the first node? Yes, no? We probably need to do that here because we've got I1. And what is I1 equal to? The current going in, but we don't necessarily know what that is. So let's do another nodal analysis. And we've already got this one over here that said V1 times 3/4 S equals V2 times 6S plus 3 over 4S. That was the result of simplifying down our second nodal equation. Our first nodal equation, this is V1. So the current into the node is I1, right? Isn't that current into the node? And the current out of the node, V1 over 2/3 S. And then plus V1 minus V2 times 4S over 3, right? So let's go ahead and solve this for V1. So we have I1 plus V2 times 3 over 4S is going to be equal to V1 times 3 over 2S plus 3 over 4S. Anybody confused as to how I got that? So now I'm going to drag I1 to the other side. So V2 times 3 over 4S equals V1. And I'm going to just put this under a common denominator now. So again, that's going to be 4S. So that's going to be equal to 6S squared plus 3 minus I1. So V2 equals V1 times 6S squared plus 3 over 4S multiplied by 4S over 3 minus I1 times 4S over 3. Wait a minute. Do I want to do that? No. Actually, let me back up. I don't want to solve for V2. I want to solve for V1. Sorry about that, folks. So let's go back over here, because if I solve for V2, I'm going to lose it. So this is I1. So now let's bring V1, we'll do V1 on by itself. So we're going to have V1 equals 4S over 6S squared plus 3 times I1 plus 3 over 4S V2 times 4S over 6S squared plus 3. Okay? So I can get rid of that. I'll divide out the 3. And what I'll end up with is 4S over 6S squared plus 3 times I1 plus V2 times 1 over 2S squared plus 1. Now I can take this whole thing and substitute it in over here. So I've got 3 over 4S times 4S plus, and now let me put the bracket here. I'm substituting that for V1. Yep. So you see right here, I'm multiplying it by 3 over 4s. Okay. So that's plus V2 times 1 over 2s squared plus 1. And that's going to equal V2 times that term. Now I only have I1 and V2 in my equation, so I've got my transfer function. I just got to do a little bit of math to make this work. So let's see. So I'm left with 3I1 over 6s squared plus 3. Let me move the I1 out front so it kind of screams at us. Plus V2 times 3 over 4s times 2s squared plus 1 equals V2 times 6s plus 3 over 4s. Now I'm going to bring the V2s to the same side. So 3 over 6s squared plus 3. Actually, let's go ahead and simplify this even more. 1, 2, 1 times I1 equals V2 times 6s plus 3 over 4s minus 3 over 4 times 2s squared plus 1. Got to put this under a common denominator, right? So I have V2 times 6s plus 3 times 2s squared, 2s squared plus 1, all over 4s times 2s squared plus 1 minus 3. And now I'm ready to do my transfer function, which is V2 divided by I1 is equal to, let's see, so that is 6s plus 3 times 2s squared plus 1 minus 3 over 4s times 2s squared plus 1 multiplied by 2s squared plus 1. So these terms will cancel, and then I'm left with that. Okay? So you can see sometimes it's a lot harder, right? When you have your terms that multiply out, you can end up with a little bit more of a challenging expression. But actually, I think I did this backwards, right? I did it backwards because I've got to, it's V2 over V1, so I have to multiply and invert. So I have 4s times 2s squared plus 1 all over 6s plus 3 times 2s squared plus 1 minus 3. And then I multiply this whole thing by 1 over 2s squared plus 1. So then I become 4s over 6s plus 3 times 2s squared plus 1 minus 3. And then you would just expand it out and go from there. Do you want to see me expand it out and FOIL it, the whole full Monty, or not?
Sure.
All right. So that is equal to 4s. So I have 12s cubed, right, when I FOIL. And then I've got, let's see, I've got 6s squared. So then I have plus 6s squared for the inner. The outer is plus 6s.
Hmm.
What's that? Yes. Wait a minute. So there's 3s. So I do first, outer. That's the 6s. Inner, and then last, right?
Question.
Yes.
Where'd you get the 2s squared plus 1 from? Because
Because it's over here, right?
I only got 2s plus 1 when I did it. So I'm not sure how you got the square term of the s there. I'm sorry.
It's okay. It's all the way from here. When I put this under a common denominator right here, you can see the common denominator is 4s. So I
Yeah.
have to multiply this by 2s. That's where I get the s squared.
I'm just trying to figure out where I went wrong.
But you can see it's a lot of algebra, right? But it's still just algebra.
Yeah.
So picking, a transfer function that is not too complicated isn't bad. But this is still way less work. It really is just algebra. And if you practice algebra a lot, you get pretty good at these things. There's nothing here that I did that's like, oh my God, he is amazing at algebra. It's just like, no, it's just algebra. It's like I just followed all the rules. Okay. That's transfer functions. It's still a transfer function. It's complicated, way more complicated than V2 over V1, but sometimes they are. Sometimes they turn out that way. There's not much you can do about it. Okay. Any more questions for the test? But it's tomorrow. We get a note card, 9 to 11:50, right? In this room, unless you've already let me know on TV land that you're going to be doing it. Yes, sir.
Question of the polls here on that.
So let's see, we have a transfer function. So this is my transfer function, my function that I have on I've got two polynomials, one in the numerator, one in the denominator. And so now what I need to do is identify the p's or the poles and the z's or the zeros. I have 1 at -4 because if I plug in -4 there, I get 0, right? I multiply it by 0.
-2.
+1,
Mhm.
-2,
-5.
-5. For the zeros, those are in the numerator. I have 0, -1, and -3. Any others? Am I missing any poles for zeros? Nobody's saying yes or no. It's either yes or no, right?
No.
Seems like a trick question. It's a yes or no. How can that be a trick question? So the answer is yes. Remember, there's always the same number of poles and zeros, right?
Right.
So if you are missing a pole, you should never miss a pole, but if you're missing a zero, because the numbers aren't the same, you always have one additional zero at s equals infinity. So now I can plot this. Here's the real part. Here's the imaginary part. The zeros are denoted as a 0 or circle. So I have one here, one here, one here, and we don't know where this one is at infinity. So for now, we'll just put it out way over here, kind of at the end, but it could actually be in a different location. The other ones we have -4, -5. We have one at -2 and +1. Okay. What's that? Right here? That's the s equals infinity. So that's a pole zero map. These are x's.
Or whichever one. Oh, this is for this.
I'm not understanding your question. Say that again.
A variable.
But yeah, normally we use x's and o's.
Right.
That's the typical what you would see.
I think what transfer function look like,
So if we have poles or zeros in the complex plane, what type of poles or zeros do they have to have? When we have complex numbers for roots, what do they have to be? They have to be imaginary, but what else? Is that okay to have that like that? Why not, Henry? You need a complex conjugate, right?
Mhm.
So I can't have one over here and not one have there over there below because of the quadratic equation, right? If this number is complex, don't I have a plus and minus right there that I have to keep with me? So if I have a positive, I better have a negative. So if this is complex, the way that I would write it is S, let's call that minus 1. So that would be S plus 1 squared plus 2 squared, right? If we wanted to write it as a complex number without any J terms in it, we would write it there. If you don't like that, we could also write it as S plus 1, oops, S plus 1 minus J and S plus 1 plus J. These two are the same. They're exactly the same.
Wouldn't you have to have another complex pair out there since you've got more than?
Can you finish your statement or question?
Well, you have a complex pair mark.
Complex conjugate pair, yeah.
Yeah. Aren't there more of them?
No, there's two. They're right here, right? I only need to have
Okay.
two complex. I can't have three and I can't have one, but I could have four, I could have six, I could have eight. But in this case, I only have two poles that are complex.
And how did you determine that?
Well,
Just by.
because the question Austin asked was,
Hmm,
what if these X's or O's were not on the real axis? So I said, okay, let's create a couple of complex conjugate pairs. And that's what we did.
Okay.
Okay.
Would the input by this that what you put on the map or
Yes. Yep.
maybe check for like the one do how that
This is minus 1 for the real part. And this is plus 2J and minus 2J for the imaginary part, right? I should have said 2. Let's call this 1. We'll call it close enough. I said 2, but let's make it 1.
Okay. Yeah.
No, let's make it 2 because let's make it 1. So this has to be a 1 as well. So that's J and minus J. Luke?
why is the infinity on the left side and not the right side?
It's a more complicated question without having the background information, but it's all based on what we call root locus plots. And so you'll hear me say this a lot next semester as you start at a pole and you end at a 0. And so before we added these two, most likely our pole 0 maps are going to go like this, and like this, and had to end out on that direction. But that was doing what we call root locus. So normally we put it over here. But when we added these two, we probably will have poles way out over here. So now it might approach it like this. Just depends on having some familiarity with pole 0 maps. Okay, anything else? You're smiling. Does that mean yes or no?
It's not, I mean, I know we haven't even taken the exam for tomorrow, but when did you say the final was again?
It's all on student records. So if you go to, it actually will be in your Main Street calendars, but I will show you how I would get it. So if you click on final exam, you see how it says final examination schedule. So you click on it, then you look for 324. Here we are. It's the 18th from 9:30 to 11, so it's 2 weeks from today. And don't gripe about the date and the time. I have nothing to do with that. I just tell them if I want to file or not. They pick the date and the time and the classroom. Yes. Barrow's 131. This is 131, isn't it? Yeah. So yeah, I have no control over that. So if anybody's like, oh, come on, can you change the date? It's like, go talk to student records. They're the ones who set the schedule. 312 is on Tuesday, yeah. Yeah, to actually set the final exam schedule is quite a bit of work. So it's all undertaken by Office of Student Records. So if you look at the top, it actually tells you Office of Student Records, Orono and Machias. So they put their letterhead on it. It's their document. It's not ours. And that they own this. Even if you look over here, the location, studentrecords.maine.edu or umaine.edu, that has nothing to do with me. I say that because every year or every semester, someone says, can you move the final? It's like, I didn't set the final. So how can I move it if I didn't set it? So that's a hard move. You can go try to ask student records if they'll move it, but I don't know if they've ever moved one. Yes. If all the poles are in the left-hand half plane, so if all your poles are here, that's stable. Poles only. Any one here
Blowing up.
is unstable.
Anything to the right of the y-axis, it will have to be.
Anything to the right of the y-axis is an unstable. All of them in the left-hand half plane, we call it, is stable. If you have a pole on the J omega axis, that's marginally stable. And the reason why it's marginally is you need to know more information, like what the input signal is. If the input is a certain input, it could be an unstable system. We talk about what's called BIBO stability, bounded input, bounded output. If the input is bounded, then the output should be bounded for a BIBO stable system. Clearly, if we have an input that blows up, we can't guarantee that the output's not going to blow up, so we don't care about those. But if it's a bounded input, then it's a bounded output, then it's a stable system. So stable means left-hand half plane, all of them. Unstable is any in the right-hand half plane. Marginal is any on the J omega axis. Including zero, right? If this was a pole, that could be a marginally stable system. It wouldn't be because if we have an X over here, that always means it's going to be an unstable system. So like, that's the thing. If it's any pole in the right half hand plane, the whole system is unstable. If you don't have any poles in the right hand half plane, then the next thing is, do you have any in the J omega axis? Then it's marginally stable. If neither of those conditions exist, then it's a stable system. Okay. The what? The zeros doesn't matter. Nope, it's just the poles. All right, good questions. Let's finish up our Fourier. Because what I really want to do is try to simplify the math. But here's a couple of things too. I'll put up a couple of these other Fourier representations. You can create a Fourier series with just a bunch of cosine waves. Here's the representation of it. You could do it with the sine wave. And notice with the sine wave, you have to have A equals 0, so you can have no DC offset. Then we talked about, does somebody have a question? Oh, okay. So here's a couple of summaries. If it's an even or an odd function, If it's even, you only have to calculate the DC component and write the cosine Fourier series. If it's an odd function, you only need to calculate the B sub n terms and you write the sine Fourier series, okay? Don't have to find a DC offset because you will have no DC offset in an odd function. And here's the most important thing that we get out of this. This whole work is basically to derive a table based on some pretty common waveforms. And let me move this out of the way. You see some signals here, square wave, triangular, sawtooth. You can even look at half wave rectifiers. So you can actually look at what the sine wave contribution or the harmonic contributions will be. And you can actually see how for a square. Arthur, you got a question?
Yeah, they're odd numbers.
Yeah. So if you look here, here's how you would write the Fourier series. And you'll notice there's an A term. You find that from the amplitude. And then the T is the period, which should allow you to calculate omega, right? The fundamental frequency. So if you look at a diagram, you should be able to determine how to build the Fourier series without having to do all those intervals. If it's a triangular wave, same thing. Here's my A term, and here's my fundamental frequency. If it's a sawtooth, A and period makes things pretty easy. Then you have half wave, full wave, and then you have these pulses. You can see how the pulses are shown over here. So instead of having to do all those derivations, just use the table.
Okay.
Then we have something called the line spectrum. If you're old like me, you might have seen it. Back in the day, they had amplifiers or car stereos or whatever. You had something called an equalizer. You know what an equalizer is?
How many bands?
5.
Yeah.
So you used to be able to, depending on your musical tastes, you could adjust individual frequencies to have more amplification or less amplification. I don't know why they called it an equalizer, but that's what they called it. So now when you take your phone or you take your highfalutin, computer to do all your audio, you pick different modes. I want rock, I want jazz, I want classical. And then they will adjust based on what the typical user likes to listen to. Do they raise up the high frequencies? Do they raise up the low frequencies? On and on and on and on and on. So you get an equalizer is basically just listing what those harmonic contributions are. So in a periodic, like if you had a song, and it's not necessarily periodic, but if you have a song, you actually would have those waveforms going up or down. And you can actually see them bouncing around. So if you want to, you can change the power levels or the amplification of the power levels based on that. So when you see somebody on a soundboard and they're sliding buttons up and down, that's what they're doing. They're bringing in a sound, so they might fade in a sound or fade out a sound. And how do they fade it in and out? Sometimes it's a specific track, but other times they're like, you know what? That symbol is not, I can't quite hear it. And so they know what the frequency of the symbols are. So they might be able to boost it up a little bit, or they actually will have a specific channel and they can bring that in and they can boost up that individual channel. So mixing boards sometimes take a lot of different audio and put it together, but you also can amplify different frequencies. So if you want, if you're listening to a harder, pounding bass, you might bump up that specific frequency. Right? So I should have, if I had time this morning, I actually had a meeting before I came to class. I was going to play a song and you could have seen like the different frequencies. I was going to play Seven Nation Army. I don't know if anybody knows what that song is, but it's got a kind of a heavy bass line and a heavy drum. But the guy who sings it has a higher pitched voice. And you could see how when they start off the song, it's kind of heavy bass. So it's really low frequency. And then when he starts singing, you can see some of the higher frequency stuff come up. And that's all, you can all tell that just by looking at essentially what an equalizer plot is. This is the more official term that we call it. We just call it a spectrum, a frequency spectrum plot. And this tells us a lot of information. So we have an audio application, but we have way more important applications. Up first, let's do this example. If I have a square wave which is here. And I've teased out the amplitude, capital A. And I know what the period is, 1 millisecond, or my frequency is 1/1 milliseconds or 1 kilohertz. Can you build the line spectrum plot for the frequencies less than 10 kilohertz? Here's our base equation, right? This is just stolen from the table. Now we need to get up until we get to 2 pi times 10K, because that's 10,000 kilohertz, or whatever that works out to be, 6,140, no, 61,040 kiloradians per second is how we would do that. So we just start plugging in. This is just an Excel table. I put in the harmonic with a specific frequency. Then I did the radians per second, and then I did the amplitude using this equation here. 4a divided by pi. 4a divided by pi times 1/3. 4a over pi times 1/5. And you'll notice the sign alternates here. That's what I have here. Notice plus, minus, all the way through. And so you can see the fundamental has most of the power. It has 6 times the amount of power that the third harmonic has. And since a square wave is an odd, right? You can see it only has the odd harmonics. You don't have any even harmonics in there. No 2, no 4, no 6, etc., etc. Here's a plot. How did I get that? I got it from Excel. Oh, not Excel, from MATLAB. So
Excel should do it too, though.
Excel would do it, yeah. But you can see this is, instead of using A, I just used K. So K is equal to 1, whatever. So in our notes, we had an amplitude of 10 volt. So let's change this to 10 volts. So K is equal to 10. My period here, I went from -1 to 1. So that's actually not 10 kilohertz. That's just a bunch of plots. Let me see if I have it in Excel. Here we go. I actually did it in Excel too. So you can do it in MATLAB or Excel. The MATLAB one is the more sophisticated one. So here is my period. Here's my example. Here's T. Then I calculate the frequency directly from T, right? It's 1/1 millisecond. Calculate omega, right? 62 or 6.2K. Here's my amplitude. Here's that table that I built. Here are all the different values that I have. And then here's my spectrum plot for the first 17, right? Anything below that value. You can see a lot of power here, not much here. And I did one-sided. So even though it shows -2, that still has power in it. So we would show that as a positive number, and then you can see it drop down from there. And then let's go ahead and start building. So this is what the waveform looks like with one harmonic. Did I put the 10? Guess I didn't. I'll have it over here. Let's go ahead and plot the sum of those. So I'm going to do the same plot over here. So you can see that this is n is equal to 1, right? I only have that fundamental, and you can see it can't be just 1. It's got to be all H6 to L6. So actually this is up to 9. So this does do up to the first 9. So it's not 1, it's 10. In Excel, it's much easier to do it in Excel. If I run this and do the plot, wait till it wakes up. So this is 17. let's do 171. Anybody know why I did 171 and not 170?
Odd.
It's got to be odd. Yeah, it can't be even. How's that look?
Yep.
A lot better, right?
Yeah.
Let's go even more.
Oh,
Hardly any change. But this is doing all the way up to the harmonics up to 17,111. Let's
nice.
go one more. Almost don't even get any of that little change. And the reason why you need so many harmonics for a square wave is that's a discontinuity. You go from -10 to +10 instantaneously. That takes a lot of additions of sine waves to cancel that out. That's why when we only go to 17, you see a lot of ringing around that point. It's working hard to get there, but it is getting closer and closer. Remember the whole thing about Fourier? You're supposed to have an infinite number of harmonics to fully and faithfully replicate it. We saw we were getting reasonably close. Like I don't know, you can tell me, does that look like a sine wave? A little bit, but not great, right? So if I do, 171, that's pretty good for me. So I need a lot of them, but yeah, that's not too bad. But square waves are the worst because look at the power levels that I have here. I'm still at 0.748 of the contribution. That's a pretty big contribution. So square waves are really hard to replicate. You get a lot of harmonics, which thanks to computers today, that's what exactly the power system experiences. Switched mode power supplies, that's what they do. They chop up a waveform with all these on, off, and they get really pretty bad harmonics. So a little bit of background on where this comes from.
I was gonna say, if you have a good enough scope, you can see some of those transient in a square wave.
Yep. Yeah, if you zoom in, if it samples fast enough, you can see it, but it also has to do with the quality of the power supply. If it's a good quality power supply, it can do it pretty easily. Like our function generators down in the basement, those are like $2,000 a piece. Those do a pretty good job of clipping off the ends. And this is if you wanted to use a complex number, so you have a J term. So now C is going to be a complex number, which adds the sines and the cosines together. So if you wanted to do this one, you would just add the terms together. Pulse train. How do you apply this stuff? One of the things, and I told you about in this class already, is vibrations analysis. Like you can tell if a bearing is starting to fail or something is in the windings are starting to fail just by doing a Fourier series. And so most of the time, what you'll experience it is you'll look at Fourier series analysis for a lot of vibrations. So seismic activity, like if you ever looked at, when they figure out the Richter scale and the power of an earthquake, they have accelerometers basically monitoring the ground all over the place in certain strategic points. And then they're always monitoring, and you can actually see the oscillation. And so they have to pull the oscillations to figure out, what was the oscillatory frequency of that. It's not periodic, right? Because the Earth doesn't keep moving back and forth, but you can get a lot of information from there. So here's one that I'll just do this experience because this was something that I was personally involved with. But this was in Western Massachusetts, a transformer, big transformer, 666 MVA transformer was energized, and it tripped just like that. So they were doing maintenance on the system. They had taken the transformer out of service to do maintenance, so they de-energized it. They were done with the outage, and they wanted to close back the transformer. They closed in, energized the transformer, and it instantaneously caused a differential trip. It tripped instantaneously. Actually, no, that was on neutral overcurrent. It tripped on neutral overcurrent. I was like, oh, this is a 660 MVA. This is inside of a mountain. So repairing it was not easy. And 660 MVA probably take you 2 years to rebuild it. So they would have been shut down for a very long period of time. So I was called in to look at this, figure out what exactly is happening, because these are the 3-phase currents that were recorded by the relay. You can see the energization up front and then the de-energization, because at that point the device had tripped. So that's after what, 5 or 6 cycles? So you can see a high level of current, but is this a problem? I don't know. And look at the voltage, 345 to 13.8 kV. So this was energized at 345. So obviously they had some pretty serious concerns about the transformer. Well, what ended up happening is they would, so here's the harmonics that you'd actually see when you energize a transformer. Look at the 5th, 3rd, and 4th, pretty darn small. Look at the 2nd. The 2nd was so high, or is so high, to indicate that you don't actually have a fault inside the transformer. You're just energizing the transformer. And that exists for about 120 milliseconds. And so the fix for this transformer was to block it from operating the trip signal when it was being energized. Because when it's energized, you get all this current going in, but no current going out. So it was tripping because it's like, hey, there's a problem here. But if we monitor the 2nd harmonic, we would actually stop the device from tripping because it was being energized. And so that what was added in. We used the 2nd harmonic to block the differential element from tripping the transformer. And interestingly enough, there were 2 relays. There was one GE and one SEL relay that were set up. And they actually had 2nd harmonic blocking enabled. The problem is the GE needed 2 out of the 3 phases to show high 2nd harmonic to block it. The Schweitzer only needed to have 1. So any 2nd harmonic component would trip. And if you look back over here, you can only see that phase A, or whatever the blue one is, I don't know if that's A or C, that's the one that was kind of high. The other 2, see if I can show you this one right here. You can see that that's got some harmonic component. So that's the one that only had a 2nd harmonic that was high. So the Schweitzer relay didn't trip because it was blocked from operation. The GE needed 2 out of the 3 to show a 2nd harmonic current was too high. It didn't happen, so it tripped the relay. So the fix was we had to add a bunch of logic into the relay to block it from operation. This is basically what we implemented in the GE relay. We utilized the 2nd harmonic blocking. That's what this is right here. And this is based on, it's kind of hard to tell, but it's the 2nd harmonic component that would come in here. You can see it says 2nd harmonic, 4th harmonic, and 5th harmonic. Those elements would come in there. And if they were above those thresholds that you could set, it would block operation. So we implemented it, and then the transformer's been running for the past 5 years. They've energized it, de-energized it, no problems with the transformer. But it's a little shaky when you energize, $5 million transformer. It's going to be shut down for 2 years, and everybody's looking at you. Can we energize it again? Can we test it again? And they're looking at you as the expert to say, yes, it shouldn't be any problem. They're like, well, I don't know, it's just looking at it, it looks fine from the outside, but on the inside, you don't know what's going on. So that's where you've got to do a little bit of understanding. And that's why it's really helpful to have some of this, because even though we don't need to be experts at Fourier, we still would go ahead and do that. So that's a specific application for electric circuits. Yes, sir.
So the harmonic current affects the relay, obviously. But that would be damage to the transformer.
No, when you energize a transformer, it gets a 2nd harmonic. And it doesn't affect the relay. The relay has all the currents that go in.
With the relay.
It calculates what the 2nd harmonic would be, and then you make a decision about tripping or not based on the 2nd harmonic. Yep. So again, that's all testing that's been done over the years. People have figured out, wow, this waveform looks really weird. Let's put it through a Fourier series to figure out what's going on. A lot of transformer energization, a lot of transformer testing is done to figure out, hey, what are the harmonic components? Should they be fixed, or is it broken, or whatever? So that's the type of thing you see. We've already talked about vibration. And the last thing we'll cover the semester because on Tuesday, right, we'll go over the exam and Thursday will be the final exam review. But the Fourier transform is if you have a non-periodic signal. So this is continuous. There are no harmonics. So you have a continuous pattern the entire way. Looks similar, but slightly different than here. So, yeah, I'm not going to talk about that. That's it. Be full of information. Probably a lot different than any of your previous classes, right? But we do a lot of calculus to get from point A to point B. And hopefully it makes you a better, you know, more solid fundamental understanding of electric circuit analysis. All right, any questions?
Yeah, are we gonna have any of this for you? Series?
I still got to figure that out if we're going to put that on the final or not.
Oh, okay.
It'd be very basic. You would not be expecting you to do integration to get that.
But not on the exam.
Not an exam tomorrow. Tomorrow is just going to be Fourier, Laplace, and the application of Laplace to circuit analysis. And pole zero maps and transfer functions, but that's all kind of the same thing. And this is the book. I'll put this up here. Let's see if you can see it. Maybe you can't zoom in.
Focus. It thinks it's the background.
I can't get my head out of the way. Move my head in. See.
Yeah, it's treating it like the background, I think.
Oh, yeah. Well, it's called Network Analysis with Applications by William Stanley. This book is out of print, but if you can get a copy of it, it's really good.
Nice.
Really helps tie a lot of the circuit analysis stuff together. Okay, any questions?
I'll probably have some at 3 in the morning, I guarantee that.
Well, I was up at 4:20 this morning. My son had to leave to go to Belfast to go get surgery. So
Oof.
we were up early. Just had to get tubes in his ears. It's not like it's cancer or anything like that. I mean, it's still surgery, but
Yeah.
it's not, you know, I'm not being flip about it. I'm just saying in terms of the level of seriousness, it's pretty benign. And his doctor already told him, it's like, yeah, if you feel good, you can do, he's got basketball practice tonight at 6:30. He can do that. He can do whatever he wants.
So, good. The Austrian forms. I'm just gonna write it right here real quick.
You don't want to write it on TV land so people in TV land can see it?
Yeah, that's it.
Come on over here.
Oh, well, you're right.
I don't know what you're gonna write.
This, the touch screen.
You got to use the pen.
Okay.
Henry's going to be a professional pitcher. We talked about that before.
No, we tried that out. Let me go. So if we have this partial fraction,
Don't forget this.
yes, absolutely. And we're trying to put that into a sine wave time domain.
Yep.
You would need to take the 3, put it over,
I need to multiply this by 3
and that, okay.
and divide that by 3.
So my b to the angle of theta is going to be divided by 3 at the end of the equation.
Right, because this over here is omega. So you need to make sure that you have omega there. That's what the Laplace table
Okay.
says. This, for the sine wave, has to be omega there.
Okay.
So you just multiply it in the end and then you divide it.
I was just confused. If you and Mark kind of do it a little bit different way. He likes to take away all the denominators, and
Oh,
you guys do different algebra, so it's not makes sense.
okay.
Thank you.
I'm not sure how he does it. I just basically show you if I need omega over here, I better put omega over there. So I don't know how Mark does it exactly, but I'm trying to scream at you saying, here's where omega is. So I'm going to put it over there as well.
Thank you.
Yes, sir. Yes. Yep. You'll have everything you need. You've only got a note card, so I'm not going to expect you to have the table on that. 5 or 6. If you look at the handout, I mean the exam review, and thank you for getting me to put the correct one up there, it does have the details. All right, anything else? Was I sharing the screen for that? I don't know.
No,
No.
So somebody had a question. Let me share it real quick. And all they said was if it's here's their base formula, and then we said you need to have a 3 here. So you got to put it over there as well. And I just said that that's equal to omega. So if you have complex, if you have a b at an angle of theta, which means you're going to have a sine term, just make sure you put the omega in the numerator. Don't forget that. That's a pretty common mistake.
Mhm.
All right. Well, if there's nothing else, have a great day. I'll see everybody with smiles on their faces tomorrow morning. Take care, everyone.
yep.
Thank you.
Thank you, Paul.
Yep.
Thanks.
Thanks,
See you tomorrow.
Brad. Thanks, guys.
Yeah, we'll make it